Hello all OpenFoamers, welcome to this video discussion of what do you call that, GHD multi-region foam, where we are now looking at adding layers to our sphere mesh. So originally we were talking about wanting to add layers according to the sphere patch. So yeah, this is what we were left with in the last video roughly, where we tried to use this sphere STL. Alright, we use this sphere refinement surface, the same refinement surface here, to try and to get the mesh that we wanted. And if we were to run the all run serial pre, yeah, if I were to run this all run serial pre, we go to the snappy hex mesh. Okay, this one was a yeah, go to that first. Where is it? It's in the snappy layer add case. Okay, so this I can delete, this I can delete. Alright, so I want to look at wireframe. Now add a filter, apply, add filter, and do the slice filter, apply a slice filter, turn this off, and I'll change this to surface with edges, and you can see that it's not working. So where is the problem? Okay, so we can take a look at the log snappy hex mesh, and this is where you will find it. Okay, right, so foam warning, function foam void snappy driver, do snap blah 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 blah, did not successfully snap mesh. Okay, that's one. So okay, there was no message over here, it seems. Okay, let's try again. Maybe, yeah, cause yeah, somehow it didn't give the correct error message I wanted. But okay, let me see. Let me use the snappy hex mesh tick, and we try to use the STL file. Okay, sphere OpenFoam STL. Okay, and I'll page down to here, and I will use this and quit, save and quit. Okay, all clean, all run serial pre, put an N. Okay, so I read the log of the snappy hex mesh. Yes, okay, this is the correct warning I wanted to show you. Foam warning, okay, cannot find patch or groups names matching sphere OpenFoam.stl. Means that the name you are given is invalid. So layer specification for OpenFoam sphere.stl does not match any patch. Valid patches are these 9: min max y, min x, max x, min y, min z, max z, sphere, sphere to oil, and oil to sphere. So just now we were using the sphere patch, but it seemingly didn't do what we wanted. So instead we can use the two patches here, sphere to oil and oil to sphere. Now which one is the one we want to do? Okay, so remember we were splitting our mesh into two parts, right? So we have our box, and then we have our little sphere here. Now let's say you're in the oil region. So the oil region will have all the 4 boundaries. And how then will it name this boundary? This boundary is called oil to sphere. Okay. So this boundary is called oil to sphere if you are talking about the oil region. So definitely the boundary, the patch we want to talk about is this patch called oil to sphere. So apparently I was wrong. There was an oil to sphere patch that's available for doing some of these generation. What kind of generation? The layer addition. So oil to sphere is definitely viable. We can write that into our snappy hex mesh. So VI system, snappy hex mesh dictionary, we can do oil to sphere. Because sphere to oil will be you looking from the solid here, you looking from the solid sphere, and then this outside boundary will be called sphere to oil. So the first word is where the region is actually. So the region for oil will use the boundary condition oil to sphere, and the region that is sphere will use the boundary condition or the patch sphere to oil. Alright, so that's how the nomenclature is. So let's do a sphere to oil here, and save and quit. We do a cleanup, and we do a all run serial pre behind the background. Okay, and we can just do a simple F5 to reload. Okay, and then you take a look at the places here. You look at this. The layers are pretty nice over here. You can see that these layers are added pretty nicely. Okay. Ooh, let me reset. Okay, we see that the let's see, the slice plot should be, let me use a wireframe instead. Okay, maybe that sort of helps, but not really help. Okay, surface with edges. Okay, so now what we see is this mesh with the layering added. You can see it conforms very nicely to the spherical surface. Okay, conforms very nicely to this spherical surface. So this is the general shape that we want. Though if you take a closer look, it looks as if the mesh at the outside is thinner than the mesh on the inside. But no matter, it is still pretty much, it's somewhat of what we want. And of course we can run a simple test to see what the heat transfer coefficient is like for this kind of boundary layer. So we can go and take a look at this. We can do an all clean. We can do an all run serial. We put it in the background. Okay. So we can kind of speed up the calculations that I'm doing here. It's going to run CHT multi-region foam. Yeah, log.cht multi-region foam. Okay, it's all looking nice. You can see that time steps are very small, and we take a look. The iteration number is basically the maximum. Why is that? Look at the final residuals. They are 2 times 10 to the 9 and 5 times 10 to the 9 for PRGH. And of course for UX, UY, UZ, and H, they are way less than 1 times 10 to the minus 9. So we see that these PRGH residuals are actually controlling, the degree of how, it's no matter how you iterate, the final residual doesn't go below 1 times 10 to the power of 9. So there are a few things we can do with with this, and basically this are done in the FV solution. Alright, so we don't need a 1 times 10 to the power of 9 kind of a tolerance, so we can change it to 1 times 10 to the 5. It's still workable. Alright, so you can go here, 1 times 10 to the 5 times 10 to the 5, 1 times 10 to the 5. Alright, so this guys, I can also leave it as such, 1 times 10 to the minus 9. Relaxation factor, I can change it back to something a lot higher so that the calculations will go faster. Okay, so 0.4 is a pretty decent relaxation factor. It should enable the stability of the problem, but at the same time, doing 0.4 instead of 0.0001, that should be able to speed up the calculation significantly. Okay, so let's look at the logs CHT multi-region phone to see whether the calculations are speeding up. Okay, so looks like it should be reading the new file soon. Okay, good. It's speeding up significantly. So yeah, you can see at about time equals 0.5 seconds in the simulation time. We see that the heat transfer coefficient is minus 1.64, which is a lot higher than what we originally had. Okay, and we look at the number of iterations. Okay, should be on top. Number of iterations 1000. Yeah, okay, see, look at this one, 0.1919 seconds in clock simulation time. See, the oil coron number is such and such, the sphere diffusion number is such and such. FV solution has been changed so that you can see the number of iterations drops because the tolerance for error is higher. I made it so that the calculations proceed a lot faster. So you see, by the time now the thing is finished, so that speeds up a lot the data significantly. Okay, so let's take a look at the data. Okay, that's the most important. Yeah, that's the most important. Take a look at the data. The data is inside the post-processing file. Post-processing, oil average heat transfer coefficient, surface field value data. And we take a look at the time here. You see it's a minus 1.6843 times 10 to the minus 2. So these coefficients, if you take a look, originally we had our heat flux data. Yeah, heat flux data, our average heat transfer coefficient was about 75. But now that we've made the mesh a little finer, our heat transfer coefficient at 0.5 seconds has almost doubled. You see, minus 1.68 is double of minus 75. So indeed, making the mesh finer does help, or making the mesh better. It does help with the calculations, and it makes the heat transfer coefficient higher. And if you take a look at here, okay, if let's say we change it to 150, for example, because that's very close to where we are, we can see that the original graph was here, where we had 75 in the beginning. And then, okay, remember this is where the original point was. We change it to 150, which is close to where we are. You see, it's much closer. It's much closer to the actual correlation Nusselt number as compared to the Rayleigh number. So this is a very interesting phenomena that we are looking at, and that is something, it is good to consider when we do the simulation. So we see that this is actually going to help. So I mean, just for completeness sake, I want to run this for 1000 seconds. Okay, control dictionary. Let's run this for 1000 seconds. Okay, so CHT multi-region foam. I want to go long CHT multi-region foam. Okay, so basically I'm going to extract data every time we run. I'll put it in the background as well. So let's go to control dictionary, and we change the write interval from 0.5 maybe to once every 5 seconds. Okay, or maybe once every 2 seconds, for example. So that should be able to speed it up a little bit. And let's take a look at our convection plume, at least with this mesh. Okay, we'll try reloading with the F5 button. Okay, so there should be a T and a U, and here also there should be a T. Alright, so good. Alright, so I can change the custom data range. So I want to change to 320, for example, so it's easier for us to see. And we go and play. Okay, see, look at that. There is some diffusion of the temperature. Okay, it's pretty strange. I don't remember seeing all these funny time frames, but okay. Right. Let's delete. It's kind of running in the funny time frames, which I don't really understand, but okay. Touch sphere.foam, and we will see that see this one, snappy layer add case. T is a wireframe, and we'll add a filter, slice filter. Okay, slice filter should go with T, and we can go with a surface with edges, or just a surface, and see how it looks. It looks a lot more even, the heating, but it's still not quite perfect. You can see the boundary layer actually heating up. Rescale this. Okay, so yeah, you can see the sphere is actually cooling down. Not a problem. Yeah, so okay. This is a surface with edges. Okay. It's an interesting case. Take a look here. We are actually doing sphere to oil. So this is inside the within the sphere itself. Okay, so ignore what I've been talking about. I think I made a mistake here. We actually added layers inside the sphere. Okay, we added layers inside the solid region, not in the liquid region. So I'll have to cancel this simulation. Okay, and how do we? Okay, and not only cancel the simulation, I'd like to also change the mesh of the oil layer. So okay, this is correct, where we have all of this what do you call that? Yeah, all of this meshes here, and that does help with the heat transfer coefficient. But I think we need to add layer in the oil region as well. So first thing first, we want to cancel this process and then restart. But of course, it's very interesting to note that just increasing the mesh quality of the solid region, it seems to increase our heat transfer coefficient already. So you can see even it's not just the liquid portion that's important, even the solid region, getting the mesh of the solid region pretty resolved well. It does help with the heat transfer coefficient. Okay, so yeah, let's redo this, and yeah, I'm gonna cancel this. Okay, already done that. Okay, how to add processes in Ubuntu. Okay, so this is the one. Force close a project program in Ubuntu. Okay. Kill all command is used to kill the program. Okay, so to view the list of running processes, we use PS and A. PS-A. So there are two versions of CHT multi-region form running. One I'm just running for my own experiments. One I'm running for this video, which is process 31193. If you can take a look at the ones before, 31193 is this one. This is actually running in the background. Okay, so next thing. Okay, so this one I'll just put it inside the description. So to kill a process using its PID, enter the kill all command followed by the PID, meaning to say the process number. So what I can do, I can write kill all. Okay, kill all. The process ID is 31193. 31193. 31193. Okay, process is not found. PS-A. Okay. Okay, it says here that killing a process using its PID does not always work. If it doesn't work for you, you can use the process name to kill the process. Enter the kill all command followed by the name. Okay. So let's go take a look. Okay, if I do that, then CHT multi-region form will be cancelled. All right. Okay, PS-A. Maybe I do the kill all. Oh, all run serial. Okay, I can do a kill all. CHT multi-region. No process found. Okay. Alright, I found another website. They say you can try kill and then you run the ID. Okay, so let me try kill 31193. Terminated. Alright, so this is the correct one. So this one I can close. So the way is not kill all, it's kill then the program number. Okay, so that killed the process. Alright. Yeah, but this is very interesting in the sense that, okay, even if I just change the mesh of the solid region a little bit, it increases the results drastically. Now let me add the liquid one as well. So let's go to System, SnappyX Mesh Dictionary. Okay, I use sphere to oil. I should have done oil to sphere. Okay, yeah, oil to sphere is for the liquid region. So that was correct. So sphere to oil is for the solid region. That's why the mesh looked a little inverted just now, because I was looking at the solid region and not the liquid region. So that's a mistake just now. But now it should be running right. And I'll do the orange serial end. Excuse me. Okay, so we can touch sphere.foam, and of course I can change the orange serial. Next time I want to include touch sphere.foam. Okay, so the next time we can just start looking straight away, okay, as it's running. So I'm gonna delete this and delete this. Okay, apply, and let's take a look at T. Let's add a slice filter. Alright, and we'll see the temperature. Apply, and we'll use surface with edges. Okay, so now it's looking a little funny because now the whole place is like, yeah, they have this kind of a funny meshing thing. But the place near the boundary layers is very well resolved, so it should look a little smooth, more smooth. Okay, so that's the point we want. That's the important point. Okay, so we just do a reload. So it's up to 10 seconds now. Yeah, so you see, look at the boundary layer. It's now going in a circular fashion instead of having those jagged edges, because we made the mesh. We made the mesh very much more suitable for this. So you see, so simple things such as meshing does make a lot of difference. So let's take a look at let's take a look at the heat transfer coefficients in the post-processing. Average sphere heat transfer coefficient, surface value data. So it's about 165, give or take. All right, 165 at about 2 seconds, right? And the heat transfer coefficient was pretty high as compared to what we had before. And the temperature was dropping, temperature at 10 seconds. Here is 486 Kelvin, whereas previously at 10 seconds, our temperature was at 493. So the temperature is dropping a lot more sharply, as it would be with a higher, heat transfer coefficient. So I'm just gonna let this thing run. Yeah. So at least for this demonstration, it shows you that making your boundary layers for your sphere for this natural convection case, it does make the results, I mean, from for the Nusselt number, it matches the correlation better. So this is something we need to be very mindful of, especially the mesh near the boundary layer. So next time, in the next few iterations, we can talk about refining this boundary layer mesh even more, because now it's still pretty thick. You can see the boundary layer is still pretty thick, and we'll want to do a lot more refinement around like this area, this area which I zoom in. We want to do some more refinement here so that we can better resolve the boundary layer and get more accurate results. So of course we'll just keep refining until there is not there won't be a there will not be any additional benefit from doing so. And of course we want to stop before we run into stability issues like we did last time. So conclusion is that we need to take a look at this boundary layer very carefully. But thanks for watching. I'll see you guys next time. It's a very, very good tutorial to go through. And next time we'll talk about even more layer addition, okay, to refine this mesh. Thanks for watching.